The Hubble Space Telescope was launched with an aberration in its primary mirror that caused severely degraded the image quality, and it was a disaster for astronomy, but a great opportunity for image processors. Here we see an image of the raw Hubble data, and then the image reconstructed with various deconvolution algorithms. So the top one here is a simple Richardson Lucy algorithm that we'll talk about today. Happily, the corrective optics was installed on Hubble. Here you see Catherine Thornton lifting the corrective optics into the Hubble and installing it in 1993. And then happily after that, the captured images were greatly improved, as you see here, comparing the original degraded image of a particular galaxy M100 and its recovered image after the installation optics were installed. One thing that you'll see that we'll talk about later in the course is that it's hard to beat good optics. So computational imaging is not a replacement for good physical sampling, but it's also necessary to use computational imaging as the last step in image estimation. Here's a more modern telescope. Here we have the James Webb Space Telescope. The James Webb has a very characteristic point spread function, this six-sided version. As we talked about at the beginning of our series of discussions in Chapter 3, you never really want to look at raw data. You should always process and try to get a better estimate of the underlying data. You can do that with James Webb data. Here's an example of a recent study showing deconvolution on images from the James Webb mid-infrared imager module, and you see that the image is improved after deconvolution. Let's talk, so in the last couple lectures, we talked first about linear regression, and then we talked about an iterative method for solving the linear regression problem using Lasso. We began Chapter 3 with a linear filter, the Wiener filter, for deconvolution. Today we'll talk about iterative algorithms for deconvolution. Computational imaging. Episode 16, expectation maximization. Suppose that there's two states that we're interested in. Let's say that it's sunny and warm. A is that it's sunny, B is that it's warm. The probability that it's sunny and warm is equal to A, probability A, the probability that it's sunny, and probability that B, that it's warm given that it's sunny. So this would be probability of A times probability of B given A. Now, we could also say what's the probability that it's warm and sunny, which would be the probability that it's warm and the probability that it's sunny given that it's warm. Those two probabilities, the probability that it's sunny and warm, are equal to each other, whichever way we orient the states. So we can say the probability of B times the probability of A given B is equal to the probability of A times the probability of B given A. That's Bayes' theorem. Very famous theorem from a couple hundred years ago that has all kinds of interesting implications. One of the things is that if we know the probability of A and the probability of B given A and the probability of B, we can calculate the conditional probability of A given B. Now, how does this relate to imaging? Well, back a few discussions ago in episode 10, we considered the process of finding a hidden parameter, x naught, from the distribution of our measurements. So this is our impulse response, h of x and x naught. We treat that in some way as a distribution for x naught. So this is essentially the probability of x naught. And back in episode 10, we then derived the Fisher information for this system, and we found the estimation error we would get under choosing the maximum likelihood, where we effectively look at this as a probability distribution and choose the most likely value of x naught from this distribution. More broadly, we can treat the distribution, the impulse response, h of x, y, as the probability distribution on this hidden parameter x in the distribution in y space. So we get a distribution g, our measurements of y, that has some form. It is ultimately going to be the impulse response h of x, y for a single impulse. And then we have a second distribution, f of x, which also is distributed over some space. Now, we can imagine an inverse operator, h tilde of xy, that would be the conditional probability of x given y. So given a g of y, what would be the operator that would take us back into the f of x space? By Bayes' theorem, treating these as distributions, we can say that g of y times this h tilde of xy is equal to f of x times h of x, y. Now, we can use Bayes' theorem to find this h tilde of xy. So h tilde of xy is equal to f of x, the distribution on x, times h of xy, then divided by g of y. Now we've written g of y in its forward model form as the integral of f of x against h of xy. Now, given h tilde of xy, we can integrate over y, g of y times h of xy. H tilde of xy integrate over all y recovers f of x. And now the only problem being that to calculate this h tilde, we need to know f of x. So we have a bit of a chicken and the egg problem that we solve by making a guess. So we guess what f of x is, and according to, let's say, some simple linear regression model or some initializer, and then we can iteratively search for f of x by finding h tilde of xy, getting a new estimate for f of x, and then inserting that into our estimate for the inverse operator and repeating this process. So this is called the expectation maximization algorithm, or the Richardson Lucy algorithm. So it's a method for solving iteratively for the deconvolution. How do you do it? Well, you can go to SK image and look for the Richardson Lucy algorithm under the restoration parameter. You need to initialize with the point spread function and the number of iterations that you want to do. You'll find that the algorithm is sensitive to the number of iterations. If you iterate too long, the image will be degraded. It can be shown that the Richardson Lucy algorithm is particularly effective in deconvolving images against Poisson noise. Here from the GitHub repository, we're comparing the Wiener filter deconvolution with the expectation maximization algorithm. So we've completed our survey of these four, the first four of the 5 basic algorithms. We looked at isomorphic imaging, and then linear regression, and then constrained linear regression. And here we've introduced our first example of a Bayesian-based estimator. These are here for historical reasons. Moving forward, these algorithms are useful as an initializer or initial guessing systems, but we can do much better in image estimation, and for that we need to use neural networks, which is the topic of our next set of lectures. What you see on the right here is ChatGPT's idea of what a neural network looks like. That's not important. We need to figure out how to use them, which we'll do in the next discussion.